Hi guys, so finally the last video in the series, CNC lathe set up and run, where I'm making these grinding wheel hubs. If you watch this video right through to the end, you'll have seen 3 videos. I'll talk a little bit about some of the Hallmark design products you can see on the website and some developments with those. Okay, cheers, catch you again. I bought this ER32 flange mount collet holder from AliExpress for only a few dollars. From memory it was $30 or $40, just as a bit of an experiment. I really didn't know whether it would be a secure way of or an accurate way of holding your work, and I've been really surprised and really impressed. It's better than a chuck. It's a fantastic way of holding work of a certain type. I'll just run this now and just have a look at how secure it is, and then I'll part it off. Alright, let's put the ER32 holder to the test. So that's 50 millimeters diameter, medium tensile, 1045 steel. We're going to part through it, and this could be an episode for America's Funniest Videos. This could be famous last words. Okay, stand back, cover your screens. There you are, you ER32 doubters. See what it can do, and see what the little Slant Pro can do. It's a rigid machine. The turret and the headstock and the spindle bearings are very well proportioned. I'm really impressed. So I just stopped short of parting it off. I'll just zip it off in the vise with a hand hacksaw, because I don't want it to fall and ding the bed. If I was making lots of them, I'd work out a part catcher for it. So for the washers, I think I've got enough leftover excess stock on the end of the short non-double parts to make the washers. This one there, 50 diameter, 20 bore, 6.5 thick. So again, just using the conversational, I produced the various little tool paths, washer face, washer OD, OD rad, spot, drill, bore, internal chamfer, and washer parting, or wasser parting I see I have. Okay, so now we've got them all combined into washer all. And how do we look at it? It looks okay. Let's run our washers. Slow it down a little bit. Yep, that looks good. didn't get good chip breaking on the boring tool, but it's okay. It's not too deep. And the parting worked out well, so that's a nice simple part. I can rattle out 10 of those, and then I'll just have the nuts to make. This little D-bit grinder is quite a cheap Chinese copy of the decal, but it's quite well made where it matters. The main spindle taper is quite nicely ground, and it's pretty concentric. You know, that's running out maybe 5 microns. That's not bad for the price bracket, and it's fairly well supported by the bearings. So it's got good potential, this grinder. I'm really pleased with the quality of it for the cost of it. So it's important that I get the hubs bored with a nice matching taper. And as near as I can measure it, you know, just with a vernier protractor, I'm getting around about 5.5 degrees a side, about 11 degrees included. There's no point in trying to measure it extremely accurately, because the method of machining it in the Tormach, using the conversational and the tool and how it cuts and all the little variables, will mean it'll be a bit of trial and error involved. And so I've made a couple of iterations, and I've now got it at 5.75 degrees a side, and that's quite nice. It's a nice snug fit, and there's no rattle on there, so I'm really pleased with that. So the procedure I've used to machine the back end of the hub after I've parted it off is to flip it round in the ER32 collet. That's a 20mm collet, and now I'm going to face it, drill it with a 10.2 drill, and then bore the taper internally. Sorry about the video quality. I don't want to run this without coolant, so you can only get a vague idea of what's going on. I'm pleased with that. Excellent. So I'll just go through the conversational, producing the code. So the two simple parts are just the facing and drilling. Well, I've covered that in the previous videos for the other side. The only new part here is the internal taper, using that same boring bar tool number 1. So I'm using the chamfering facility here, and I finished up with a 5.8 chamfer angle, worked out to be the best one. And the tool path in some ways is not ideal, because it's not normally used for taper boring, this chamfer facility, and the tool enters into the bore and then cuts on the retraction, which is a bit of a problem for a long deep chamfer, although it has some advantages such as chip clearing. So I had to adjust the depth of cut and the drill depth clearance a little bit to allow for the different retraction moves and so on. Let's have a look at the tool path. So you can see there several passes. So the tool comes in at clearance and then takes the cut on the retraction, comes back round, and so on. It works out okay. I just had to take quite light cuts and give it a bit more drill depth. You've got to be cautious because there's an additional Z move to start the tool, which would plunge into a blind hole, so you've got to adjust that. But you know, with a little bit of adjustment, it worked out well. So I started with what I thought the taper was, about 5.5, and I put it on the little shaft and it rattled slightly. It's always hard to tell which way, whether it's acute or obtuse. And so I tried one way and got it a little bit better, and then tried again. Ended up with 5.75, 5.8 was a good taper. You know, people will say, well, just use bearing blue, but bearing blue doesn't really work all that well, I've found, because you know, you can transfer it 100% even when the angle's wrong, because you tend to rock it as you turn it round inside the bore. It's better just trial and error until it's an absolute rattle-free fit. If you like the look of those inserts that I refer to as trigon inserts for the OD turning tool, they're the ISCAR WNMG 06T304. They're fantastic. 6 edges, and they last well, they stay sharp, and they do good chip breaking in steels, tool steels, medium tensile steels. Of course, it had to be the one at the bottom, didn't it? Okay, so I turned the turret around. So this Trigon tool, or WNMG, is a very strong, durable tool, especially in a good brand like ISCAR. Hard wearing and great for chip breaking. It's not a razor sharp diamond ground shape that's good for high precision finishing, but it's a durable, hard wearing tool that's good for unattended running, automatic running. It's not likely to break down or let you down or get chipped or dull. It's going to keep trucking on part after part and let you get away and do something else while the machine runs automatically. And because the included angle is fairly close to 90 degrees, it's suitable for both OD turning and facing in the one tool. That's a big advantage as well. And let's see how concentric it is. This is also important. Oh, that's really good. Pleased with that. And what's it like on the face? Yeah, that's running true. So that's a really accurate little hub now, and it'll spin the diamond wheels nice and concentric. That's really important. And for the final part, the nut, I'm going to machine out of a length of stock 35 millimeters diameter, and I'm going to put that in the Slant Pro's biggest chuck, the 6-inch chuck. And you might be thinking, well, why are you putting it, a small piece of stock, in a big chuck? You know, earlier on you were putting big pieces of stock inside a small chuck. Well, the reason for that is that the best option of all is to put your stock right inside the chuck and inside the spindle if you possibly can. But once you get above about, you know, the diameter of the bore of the spindle or the bore of the chuck, you can't do that anymore. And the body and the washer were 50 millimeters diameter, just too big to fit inside even this big bored out 6-inch chuck. So I had to use other methods, holding it beyond the end of the chuck within the jaws or in the collet when I flipped it round. But in this case, now I've gone back down to a size of 35 millimeters. I can put the stock right inside the chuck and have it ready. It's really well supported if you can do that, because there's a good long length of jaw engagement, and although it's projected out further from the spindle bearings, it's still quite well supported, and it's efficient to manufacture something out of a long length of stock and just use the same program, machine one part, part it off, slip it forward to a stop, machine the next one, and it'll run automatically, and just chop them out one at a time from the end of a long piece of stock that you advance forward each time. That, generally speaking, or usually speaking, is the best method if you can fit the stock within the chuck. You can see here with the bigger chuck, that drill, when I'm doing this stage of turning, that drill is clear now, but it was just too close in that other gang tooling bore. So if you're using big chucks, you have a very limited number of gang tooling positions. For cutting the thread on the nut, I'm going to use that high-speed steel tool. It's a nice stiff tool. It looks like about the right proportions for the job. So if you want to add a tool when you've already partly got through the job, you can put the tool setter back in, for example in this case just into the chuck, set it on the right rotational position with the bubble vial, calling this tool number 4. And in the X tool touch DRO, we enter 0 at that point. Okay, so let's say you've set all your tool offsets and your work offsets, but now you decided you want to change one of the tools. You want to add a tool, or you want to move the position of a tool, and you want to set that tool offset without affecting the existing tool and work offset settings. How you can use a tool setter to do that. Let's say tool number 7 is a new tool or a reposition tool that we want to apply after we've set all our tool and work offsets. So we'll put in the tool that we're going to use as our reference tool, tool 2. We have to close the door because it's a turret, but this could be a tool changer or gang tooling or whatever. I'm just going to show it graphically just to give you a rough idea. So we're sitting up there. Okay, so you can see that tool is approximately on the end there, and we can see that that is set on Z0 for tool 2. Now we're going to change the work offset and use a different work offset to set this new tool position, the new tool offset position relative to this master or reference tool. The best practice is not to use a tool for your reference tool, because tools vary when they get blunt or if they're repositioned. It's better to use a fixed point on the turret, gang or quick change tool post, but in practice a lot of us do use a tool, for example our main OD tool, because it projects out from the tool holder and it's quite a practical thing to do, even though it's not best practice. So I'm going to put the tool setter in now and change the work offset and just go through setting it. Okay, so we put our tool setter in there, ready to set the tool offset. Please note, I'm not trying to promote this tool setter especially. You could equally do this with a split shaft tool setter, you know, a D section. So okay, we've got a tool setter in there. We've still got our reference tool number 2 in place. Got that set up there. We've changed our work offset to G55. We're going to come into contact. Just roughly, just to give you an idea of what I'm doing, we're going to set our work offset there, Z0, back off, change to tool number 7, that's the one that we want to set the tool offset. Now we've set the position for tool 7, and tool 7 is automatically set there. We go to the tool offset DRO, we enter. So you can see the tool offset's incorrect there. Click on that twice and we've set our tool offset using this G55 setting. And if you look in the tool offsets table, you can see now tool 7 is set relative to tool 2. It's minus 265 and tool 2 is minus 260 approximately, so that's about a 5mm difference. So it's been set into the tool table using a different work offset. Now if we put the work back in again, you can graphically see that that tool has been set. Now this is just for setting the Z. The X is fine because the X is based on the center line of the lathe. You don't need to change the work offset to do that. You can use the same work offset because the tool setter is based on the center line of the lathe. So we've got tool 7 in there, we're in G54, we're in Z0, and you can see the tool is in line with the end of the stock, so that's correct. I'll just put back in our reference tool, tool number 2. And you can see that tool number 2 is also at Z0. So just quickly giving you the concept there of how you can use a different work offset to enter a new tool mid-program or without disturbing existing tool offsets settings for the Z. For the X, you can happily do it in the same work offset because it's based on the center line for both the tools and the tool setter. But obviously the tool setter is going to have a different length than the work, and you get around that by changing the work offset and going through that little procedure. Now because I've got a 6-inch chuck in there, it won't clear that drill, will it? I'll need to move that drill down to another position. Let's call that position 10, so we can set that tool up with the tool setter as well. Set it in a rotational position about there. And enter the diameter into the X tool touch DRO of the drill. So you can use the tool setter to make on the fly tool changes very conveniently. So all the washers have been machined in the lathe with the bore and the OD and the ends all concentric, but when they're parted off, that surface is unlikely to be flat and nice and smooth. So it's an ideal application for a surface grinder with a magnetic chuck, because you're reproducing a nice flat parallel surface opposite the accurately machined end surface. So you can see that's quite a quick process. Another couple of thou passes and we'll have the backs beautifully flat and all the parts of an equal thickness. A magnetic chuck and a surface grinder is perfect for this type of work. So that's just a couple of minutes work to finish the back side of the washers. And the same for the back surface of the nuts. I love grinding machines. I think of a grinding wheel as a big milling cutter with thousands of teeth. Back chamfering, the last chamfer of the nuts. Some of you might not realize you can make or buy these spacer discs that fit around the 3-jaw and allow you to position your parts nice and quickly and concentric up against the spacers. You can get them in different, well, these are ones I've made out of steel, just different thickness ground spacers, and you can put something soft like foam tape or silicone on the clearance and the gap there, so it suits different size chucks, slightly different size chucks, and it doesn't rattle. So they're really handy for quickly positioning your part concentric. You can do that in the CNC lathe as an automatic procedure using your threading tool to cut that chamfer. But I'm only making a few parts and I'm not bothering to do that. It's only a few minutes work to manually do that as a secondary operation. But if I was making hundreds of parts, I would get that move as part of the tool path to use the threading tool to cut that chamfer. The nuts have some holes in them that are driven by the pins in this machine wrench. It's a face wrench, and they go into the little holes. So I'm just going to drill those now in the Tormach. Have you seen the new Hallmark ATTP Pro? It's got a fully hard anodized body and it's unpluggable and pluggable. So you can leave the cable stored on the machine and you've got a more portable probe that's easier to dial in without the cable wrapping around it. It's just a little bit more convenient. It's the same internals as the standard ATTP. Have a look on my website. There's links to different videos on it underneath this particular YouTube channel, Thread Express. Just setting the X, Y and Z offsets, and then we can go ahead and drill those holes. Another advantage of having the Pro unpluggable is it allows me to develop a little self-contained accessory that makes the probe self-contained, so now we can use it in a manual machine as a edge finder, and it's got a lot more features than an ordinary edge finder because it can be dialed in concentric with the adjusting screws. It's got a long thin stylus, unlike an ordinary edge finder that can find its way down into hard to reach places. So it's quite a high spec edge finder, but it would obviously be an expensive edge finder, and I'm not sure if there's a market there for it or not. Please let me know in the comments below if this interests you and you can see some application for it, or if you'd be interested in something like that. Another advantage of this edge finder is that it doesn't require the work to be conductive. Ordinary edge finders, LED edge finders, require that the work is conductive of electricity and the circuit is completed through the machine. And on some machines you've got resistance through the spindle bearings and so on, and you lose a lot of the current in the circuit and you get a very dim light if it works at all. But this is completely self-contained and it just works with mechanical contact, so it would work fine on plastic parts or non-conductive parts. There may be specific applications for it that I haven't thought of. Let me know if you can think of anything. I'm not sure whether I should continue to develop this product or not. It's always really hard for me to work out whether there's a market there or not. I don't want a big chamfer on the edge of these holes because lead in can too easily become lead out. So just a tiny little break just to take away the sharp edge. A few thou deep. Well, I want to harden these 1045 nuts because the little holes that are driven by the face pin wrench will become sort of damaged over time as the pins tend to skid out, so they really would benefit from being hardened. So we've heated it up to 800 odd degrees C, and we're just going to biff that in some oil. Some people say you should harden 1045 in brine. Probably needs that to get the optimum hardness, but I just want to toughen them up. You know, if I'm up above 50 Rockwell C, I'll be happy. I've also got a couple of tool steel 01 steel washers in there that I'm going to use under the head of the screw just to stop the screw from damaging the little threaded seat. We don't need to go stone cold, although I don't think you can over harden 1045. I don't think it's a brittle steel, it's really a medium tensile steel. So let's see if that's hardened up. I might not be able to tell by filing. Compare it with a soft one. Now I'll need to center punch test it It's a good way to test it with a sharp centre punch. If it flattens the centre punch end, you know you've got above 50 Rockwell C. Yes, that's gone hard. You can see the little dimple there, and it's flattened the end of the centre punch. So that's a good way to test. A file is over 60 Rockwell C, and you can file a reasonably hard piece of steel. It's quite difficult to tell whether you've really achieved hardness, but a centre punch is a good way to be sure. A good quality centre punch, like a Starrett centre punch, will easily punch a piece of reasonably hard steel, but it won't be able to centre punch a piece of steel above about 50 Rockwell C. So it's really good for testing something that you don't need to be glass hard, but you just want reassurance that it has been hardened. And while you need a kiln to heat your parts up to red hot to harden them, a domestic oven is really good for tempering, for fine control over the lower temperatures. For example, there are the nuts that have been tempered back, and the other parts I've put in there as well, just to give them a nice colour at a couple of 100 degrees C. Well, thanks for watching those 3 videos. If you've seen something you're interested there, the lathe tool setter electronic, there's also a lathe tool setter mechanical and a lathe tool setter fixed. Have a look at the Hallmark website. I'll put a link underneath the video. Also some information there on the video, lathe tool setter fixed, how you can make your own lathe tool setter and not spend any money at all. You probably saw me introduce the Hallmark Pro with its little attachment to be used as an edge finder. This is a pluggable and unpluggable product. Having lots of fun making these things. Catch you next time. Cheers.